Hello everyone, and welcome to the Inspection Pro Hub channel, where we dive deep into the fascinating world of corrosion science and inspection. Now, whether you're an engineer, a technician, or simply someone interested in the science of materials and how we prevent failures in industries like oil and gas, manufacturing, or construction, you're in the right place. In today's video, we're going to explore a critical topic that affects the integrity of countless materials and structures: corrosion embrittlement. Specifically, we'll be focusing on the phenomenon of 885 degrees Fahrenheit embrittlement and how it impacts specific types of stainless steels and weld metals. If you've ever wondered why certain stainless steels become brittle and prone to cracking after being exposed to certain temperatures, or how to prevent catastrophic failures in high-stress environments, you're going to want to stick around. Let's begin by understanding the description of damage. 885 degrees Fahrenheit embrittlement refers to a phenomenon in stainless steels, particularly those containing a ferrite phase, where the material becomes more brittle and prone to cracking or failure after being exposed to certain temperatures, typically in the range of 600 to 1000 degrees Fahrenheit, or equal to 315 to 540 degrees Celsius. The term embrittlement is used to describe the loss of the metal's ductility and fracture toughness. Why does this happen in ferritic stainless steels? Ferritic stainless steels typically contain 10.5 to 30% of chromium and have a body-centered cubic crystal structure, and when ferritic stainless steels are exposed to the temperature range of 600 to 1000 degrees Fahrenheit, certain crystalline phases, like the sigma phase and chi phase, can form, and these phases are brittle, and their formation weakens the material, making it more susceptible to cracking. In addition, chromium carbide precipitation can occur at grain boundaries. The carbide formation depletes the surrounding areas of chromium, lowering the steel's overall resistance to corrosion and mechanical strength. In this section too, we're going to dive into the specific types of stainless steels and weld metals that are most susceptible to this phenomenon. First is 400 series stainless steels. 400 series stainless steels, including alloys such as 405, 409, 410, 410S, 430, and 446, are primarily ferritic in structure. These steels generally contain 12 to 30% of chromium as their main alloying element, and having a body-centered cubic, BCC, crystal structure. 400 series stainless steels are often used in applications where oxidation resistance and good strength at elevated temperatures are required, such as in exhaust systems and heat exchangers. However, when exposed to intermediate temperatures in the range of 600 to 1000 degrees Fahrenheit, these alloys become prone to 885 degrees Fahrenheit embrittlement. Second is duplex series stainless steels. Duplex stainless steels such as 2205, 2304, and 2507 combine a roughly equal mix of ferrite and austenite phases to achieve higher strength and enhanced resistance to corrosion, particularly in harsh environments like marine or petrochemical applications. While duplex stainless steels are highly resistant to corrosion and stress corrosion cracking, they can also suffer from embrittlement when exposed to temperatures between 600 to 1000 degrees Fahrenheit. In this temperature range, the balance of ferrite and austenite phases can be disturbed, leading to the precipitation of embrittling phases, particularly the sigma phase, which significantly reduces toughness and ductility, and this makes duplex stainless steels more susceptible to cracking and failure if they are exposed to thermal cycling or improper welding conditions that promote these phase changes. Third is austenitic stainless steel weld metals in the 300 series. Austenitic stainless steels in the 300 series, such as 304 and 316, are commonly used in welded applications due to their excellent corrosion resistance, formability, and toughness. During welding, however, these alloys typically contain a small amount of ferrite, around 5 to 10%, in the weld metal to prevent hot cracking that can occur during solidification. This ferrite is beneficial during the welding process, but when the weld metal is exposed to temperatures between 600 to 1000 degrees Fahrenheit, it can undergo a transformation into brittle phases, like the sigma phase, which can embrittle the weld. This embrittlement leads to reduced ductility and fracture toughness, making the weld joints more susceptible to cracking under stress or in service, especially in high temperature or cyclic loading conditions. Understanding the critical factors is about protecting valuable infrastructure and avoiding costly, catastrophic failures. In this section 3, we're going to explore the key influences in detail. So, let's dive in and uncover the hidden drivers behind this dangerous phenomenon. First, critical factors influencing embrittlement are alloy composition, particularly chromium content and the amount of ferrite phase, and the operating temperature. Chromium content plays a crucial role in enhancing corrosion resistance, but at elevated temperatures, typically between 600 to 1000 degrees Fahrenheit, high chromium levels can promote the formation of brittle phases like sigma phase, which degrade the material's ductility and fracture toughness. The presence of a ferrite phase, especially in ferritic and duplex stainless steels, also increases susceptibility to embrittlement at these temperatures, as ferrite can transform into brittle phases that weaken the material. The operating temperature is equally critical. Prolonged exposure to temperatures in the embrittlement range allows for phase transformations that reduce the steel's ability to absorb stress, increasing the risk of cracking and failure. Hence, proper control of both alloy composition and temperature is essential to mitigate embrittlement and maintain material integrity in high-temperature environments. Second critical factor is chromium content. Chromium content plays a critical role in the susceptibility of stainless steels to embrittlement. Alloys with lower chromium content, such as 405, 409, 410, and 410S, exhibit a reduced tendency for embrittlement compared to higher chromium materials like 430, which contain 16 to 18% of chromium, and 446, which contain 23 to 27% of chromium, and duplex stainless steels, which contain 22 to 25% of chromium, which are more vulnerable to this phenomenon. On 300 series stainless steel weld metals, although embrittlement has not been extensively observed across all, Charpy impact tests on Type 308 and Type 347H weld metals aged at around 850 to 885 degrees Fahrenheit have shown signs of embrittlement, with some samples showing impact values below 15 foot-pounds at ambient temperatures. Despite these findings, embrittlement is generally not a major concern in typical refining applications where these materials are commonly used. Third critical factor is the amount of ferrite phase in duplex stainless steels. The amount of ferrite in duplex stainless steels is a crucial factor influencing their high-temperature performance and susceptibility to embrittlement. As ferrite content increases, the material becomes more vulnerable to damage when exposed to the critical high-temperature range, which raises the ductile-to-brittle transition temperature, making it more prone to brittle fracture. To mitigate this risk, duplex stainless steels must be cooled rapidly after welding to prevent the formation of detrimental phases, such as sigma phase or delta ferrite, which can significantly impair the material's toughness and corrosion resistance. Careful control of ferrite content and cooling rates is therefore essential to maintaining the integrity of duplex stainless steels in high-temperature environments. Fourth critical factor is high-temperature exposure. High-temperature exposure is a key factor in the embrittlement of stainless steels, with damage typically occurring when materials are subjected to prolonged periods within the critical temperature range, around 885 degrees Fahrenheit. The extent of embrittlement depends on both the temperature and the duration of exposure, as damage is cumulative over time. At temperatures beyond the critical threshold, achieving maximum embrittlement may require significantly longer exposure. For example, at 600 degrees Fahrenheit, it may take thousands of hours for the embrittling phases to fully develop. Therefore, managing exposure times at elevated temperatures is critical to preventing premature failure due to embrittlement. Fifth critical factor is the duration of service in high-temperature environments. The duration of service in high-temperature environments is a crucial factor in the embrittlement of materials, as prolonged exposure to elevated temperatures can lead to significant degradation over time. In practical terms, materials exposed to temperatures ranging from 600 to 1000 degrees Fahrenheit for extended periods, typically over many years of service, are generally considered to have been affected by embrittlement. This is because such exposure can promote the formation of embrittling phases, such as the alpha prime phase, which compromise the material's toughness and mechanical properties. As a result, equipment operating in this temperature range for extended periods may experience increased vulnerability to brittle fracture and failure. Sixth critical factor is the impact of temperature fluctuations on toughness. Temperature fluctuations can significantly affect the toughness of materials, particularly when they experience rapid cooling or heating during plant shutdowns, startups, or upset conditions. While the impact on toughness may not be pronounced at the steady operating temperature, sudden drops in temperature can cause materials to become brittle, especially if they are already susceptible to embrittlement due to prior high-temperature exposure. This is because the ductile to brittle transition temperature can shift, making the material more prone to fracture under stress at lower temperatures. Hence, managing temperature variations is critical to maintaining material integrity and preventing unexpected failures during operational transitions or abnormal conditions. The last critical factor is the impact of heat treatment on embrittlement. Heat treatment plays a significant role in the potential for embrittlement in materials, particularly if they are held at or slowly cooled through the embrittlement temperature range. When materials are exposed to this critical range, typically between 600 to 1000 degrees Fahrenheit, and undergo slow cooling, it allows for the formation of embrittling phases, such as the alpha prime phase, which degrade the material's toughness and ductility. This can severely compromise the material's integrity, making it more susceptible to brittle fracture. To avoid this, heat treatment processes must be carefully controlled, ensuring that materials are rapidly cooled or quickly moved through the embrittlement range to maintain their mechanical properties and performance. Up next, in this section 4, we'll delve into units and equipment affected by 885 degrees Fahrenheit embrittlement. Units and equipment affected by embrittlement include any system where susceptible alloys, particularly ferritic stainless steels and duplex stainless steels, are exposed to temperatures within the embrittling range of approximately 600 to 1000 degrees Fahrenheit. Most refining companies, aware of this damage mechanism, limit the use of ferritic stainless steels to non-pressure boundary applications where the risk of embrittlement poses less of a hazard. By restricting these materials to less critical areas, companies can better manage potential embrittlement-related damage and enhance overall equipment reliability. Affected units and equipment commonly include fractionator trays and internals in high-temperature vessels, particularly within crude, vacuum, fluid catalytic cracking, and cooker units. These components are often exposed to temperatures that can lead to embrittlement, especially when made from ferritic stainless steels like Type 409 and 410. Failures are frequently observed during maintenance activities such as welding or straightening of vacuum tower trays, as the heat exposure in these processes can induce or worsen brittle phases in the material, making it more susceptible to cracking. Proper handling and careful control of welding practices are essential to minimize this risk and maintain equipment integrity in high-temperature environments. Duplex stainless steel heat exchanger tubes and other components exposed to temperatures above 600 degrees Fahrenheit for extended periods are particularly vulnerable to embrittlement. Duplex stainless steels are designed for use below this temperature limit, because prolonged exposure to higher temperatures can disturb the balance between the ferrite and austenite phases, leading to the formation of brittle phases such as sigma phase. This phase transformation reduces toughness and increases the risk of cracking and failure under stress. As a result, the maximum service temperature for duplex stainless steels is typically set at 600 degrees Fahrenheit to preserve their mechanical integrity and corrosion resistance in demanding environments. In this section 5, we'll explore the visual characteristics and morphology of damage to better understand its underlying causes. 885 degrees Fahrenheit embrittlement in stainless steels is a metallurgical change that results in the formation of brittle phases, reducing the material's toughness and ductility. This embrittlement does not produce visible signs that can be detected through standard visual or microscopic examination, as it affects the steel's internal structure on a level that doesn't alter its outward appearance. Instead, the damage is primarily identified by a loss in mechanical properties, particularly a reduction in impact resistance, which can increase the risk of brittle fracture under stress. Specialized testing methods that measure changes in mechanical behavior, such as impact testing, are therefore required to detect this type of embrittlement. Embrittlement at 885 degrees Fahrenheit occurs when materials are subjected to prolonged high-temperature exposure, causing microstructural changes that degrade their ductility and toughness. This process can be detected by an increase in hardness, indicating a loss of toughness and heightened brittleness. In addition to hardness tests, Bend or impact tests on service-aged samples often demonstrate reduced capacity to resist deformation or absorb energy, leading to failure. These tests are essential for identifying materials prone to embrittlement, helping ensure the reliability and integrity of components exposed to high temperatures in industrial settings. Embrittlement commonly occurs during turnarounds, startups, or shutdowns, when materials, such as 410 stainless steel, are exposed to lower temperatures where embrittlement effects are most pronounced. To restore adequate toughness in embrittled 410 stainless steel, it requires heating to around 350 degrees Fahrenheit, allowing for the recovery of its mechanical properties and reducing the risk of failure during service. Proper temperature control during these critical phases is essential to prevent embrittlement and maintain material integrity. This image showcases a sample of a material exhibiting severe embrittlement, as evidenced by the presence of intergranular cracks visible in its microstructure. These intergranular cracks occur along the grain boundaries of the material, indicating a weakening of the bonds between the grains rather than within the grains themselves. This type of cracking is a characteristic feature of embrittlement, which significantly reduces the material's ductility and fracture toughness. The visible damage highlights the potential for catastrophic failure under stress, particularly in high-temperature or chemically aggressive environments, where embrittlement mechanisms such as 885 degrees Fahrenheit embrittlement might be active. Identifying and analyzing such microstructural features are critical in evaluating the material's remaining life and ensuring structural integrity in service applications. In this section 6, we'll explore the prevention and mitigation of 885 degrees Fahrenheit embrittlement, which involves several key strategies. The most effective approach is to avoid exposing susceptible materials, particularly ferritic stainless steels, to the critical temperature range, within 600 to 1000 degrees Fahrenheit for extended periods. When this is not feasible, it is recommended to use alternative materials that are not prone to this type of embrittlement, such as austenitic stainless steels or certain nickel-based alloys. In some cases, particularly for non-pressure-containing components like trays and internals, users may accept the associated risks and address any issues during routine maintenance, balancing operational needs with safety considerations. Controlling temperatures during startup and shutdown procedures is crucial in preventing the cracking of embrittled materials. This method involves carefully managing heating and cooling rates to minimize the time spent in the critical temperature range. The effects of 885 degrees Fahrenheit embrittlement can be significantly reduced by modifying the alloy's chemical composition, particularly by adjusting the chromium content or adding stabilizing elements like titanium or niobium. This approach can enhance the material's resistance to embrittlement at the critical temperature range. However, it's important to note that these resistant materials may not always be readily available in commercial forms, which can limit their application in certain industries or for specific components. This constraint necessitates careful planning and potentially longer lead times for material procurement. One of the notable characteristics of 885 degrees Fahrenheit embrittlement is its reversibility through appropriate heat treatment. This process typically involves heating the affected material to temperatures of 1100 degrees Fahrenheit or higher, followed by rapid cooling. This heat treatment effectively dissolves the precipitates responsible for embrittlement, restoring the material's ductility and toughness. However, it's crucial to recognize that this treatment may not be practical for many equipment items due to size, complexity, or operational constraints. Furthermore, if a de-embrittled component is re-exposed to the same service conditions that caused the initial embrittlement, it will tend to re-embrittle more quickly than before, necessitating careful consideration of long-term material management strategies. In this last section, Section 7, we'll talk about inspection and monitoring of 885 degrees Fahrenheit embrittlement. Inspection and monitoring of 885 degrees Fahrenheit embrittlement present significant challenges due to the nature of this damage mechanism. Detecting this damage mechanism is challenging before equipment fails, as it develops gradually over time in service, making online inspection ineffective. The most effective and reliable method for detecting or confirming this type of embrittlement involves removing a sample of the suspect material and subjecting it to impact or bend testing. This approach is particularly useful for thin components such as tower trays, where a simple bend test failure can provide strong evidence of embrittlement. It's important to note that metallographic examination is generally not effective in identifying this damage mechanism, as the embrittlement-causing phase is often difficult to observe in the microstructure. Given these limitations, a proactive approach to inspection is crucial. This includes closely monitoring equipment exposed to the critical temperature range 600 to 1000 degrees Fahrenheit and developing targeted inspection strategies. Visual inspection can be effective in certain scenarios, particularly for non-pressure-containing components such as trays and other hardware. Cracking may become visually apparent during maintenance or repair activities, providing a clear indication of embrittlement. Visual inspection method, while straightforward, is limited to detecting damage that has already progressed to a visible stage. Field hardness testing offers a potential means of distinguishing between embrittled and non-embrittled materials. However, it's important to note that hardness testing alone is generally not definitive in diagnosing 885 degrees Fahrenheit embrittlement. Moreover, the hardness test itself can potentially induce cracking in severely embrittled materials, adding a layer of complexity to this inspection method. Hammer testing, also known as field impact testing, is considered a destructive test and should be approached with caution. This method involves tapping a suspect component with a hammer, which may cause cracking depending on the degree of embrittlement. While hammer testing can confirm that a component is not severely embrittled if it doesn't crack, or that it is embrittled if it does crack, it carries the risk of damaging the component being tested. This technique should only be used when the potential for component damage is acceptable and other non-destructive methods have been exhausted. Thank you for watching. The material discussed in this video is based on the guidelines and knowledge outlined in the API 571 standard, and all images in this video are sourced from third parties and are used for illustrative purposes. I hope this video was helpful to you. Don't forget to like, share, and subscribe so you won't miss our upcoming videos. If you have any questions, feedback, or suggestions for other topics you'd like us to cover, feel free to leave them in the comments column. See you in the next video.